afternoon to all of you to this session of thermodynamics. Now, last session we are discussing the entropy, which is one of the most important and useful concepts. So, I will repeat a part of our discussion in the last session or last class for the sake of continuity to the material of the present section. So, let us start with little recapitulation or repetition of the things which we discussed earlier, that delta S change in entropy was defined as in any process as the delta Q in a reversible process integral delta Q R by T. So, this is in a reversible process, this delta Q by T was defined as the change in entropy, which is valid for any reversible or irreversible process. This definition for the change in entropy is valid for any process, but it is defined through this quantity del Q by T in a reversible process. Well, also we recognize that for any other process delta S, that means delta S, if the process is not reversible, then how delta S relates with this quantity for the process, that delta S is greater than del Q by T. This is a repetition which I told earlier. That means the del Q by T quantities, integral of these quantities for a process is always less than delta S, which means that this is greater than this, that is delta S is greater than del Q by T for any process. Then we recognize that if a process is adiabatic and reversible, for a reversible and adiabatic process and adiabatic process, delta Q is 0 and moreover the process is reversible, that means delta QR I can write 0. So, delta S becomes 0. So, for a reversible and adiabatic process delta S is equal to 0, which gives S is constant, which tells that in a reversible adiabatic process entropy remains constant. That is why a reversible adiabatic process is known as isentropic process, But for any reversible process delta S is del Q R by T, where there is an heat transfer. That means any reversible non-adiabatic or diabatic process delta S is del Q R by T. So, we can write this in a differential form as ds is delta Q R by T. If we integrate this, we can tell that the heat transfer added or rejected in any process connecting the states 1 to 2 for a reversible one is TdS 1 to 2, okay, TdS 1 to 2. We are interested in this heat transfer added or rejected. In a reversible process, heat added or rejected connecting the state points 1 to 2 can be written like this. So, this is an useful relation in a sense that if we denote a reversible process or represent a reversible process in a TS diagram, where T is the temperature and S is the entropy, if the process is like this 1 to 2 in this direction. So, when the process is this way, where the entropy increases and temperature increases, it is a heating process where del QR is greater than 0, QR is greater than 0, for which entropy change is greater than 0, entropy increases and temperature also increases. So, it is a heating process, reversible heating process. In this case, the area under this curve intercepted on S axis gives the heat addition. Similarly, if this area, this hatched area, similarly if the process is a heat rejection reversible process, then the direction of the process is other way, that means initial point 1 here, 2 here, where the entropy is decreased because delta Q is negative there by the usual sign convention, delta S is less than 0, ds is less than 0. Then this area represents the heat rejected, which means that the area under the curve in TS plane of a reversible process represents the heat interaction quantities. And if a reversible process does not interact heat, that means reversible adiabatic process, we know entropy remains same, that means that process will be a either expansion or a compression 1 to 2 or 2 to 1, where temperature will increase or decrease. This is non-adiabatic process, this is a non-isentropic process, reversible adiabatic process, and this does not have any heat transfer, that means Q is equal to 0, QR is equal to 0. This is the line. There is no intercepted area on this TS axis. So, these are very simple. Now, again I start repetition of the earlier thing, that delta S for any process is greater than integral delta Q by T. And now, with this what we deduced earlier, that an isolated system, what is an isolated system? An isolated system is essentially adiabatic, that means delta Q is 0. System may be reversible or irreversible. System may be reversible, that means the process within this system may be reversible or irreversible. That means an isolated system where there is no heat transfer and work transfer, so it is essentially adiabatic from the heat transfer point of view. If any internal processes within the system may be reversible, may be irreversible, but delta Q is 0, and we had this, that is for an irreversible process. When it is reversible process, delta S is equal to delta QR by T. So, combining these two we wrote is delta Q by T. That means it is valid for any process. If it is reversible, equality sign holds good. If it is irreversible, greater than. Now, for an isolated system, since delta Q is 0, so delta S isolated system is greater than 0. So, this is one of the very important principles, that for an isolated system the change of entropy is greater than 0. All right. Then what we discussed, that if there is a system which interacts with a surrounding, that means if we identify a system and its interacting surrounding, that means they are interacting with each other in any directions in terms of work and heat, that is the only way by which system and surrounding can interact with each other. Then we can define an equivalent system consisting of this system and surrounding as an isolated system, or universe. This is in a limited sense, I have told, as I have told earlier, the isolated system is defined as an universe which does not have any other interactions with the rest part of the surrounding. So, this surrounding means another system which is interacting with this system. So, there may be a number of other system interacting between each other. So, a number of interacting systems can be considered together as an isolated or universe, where the systems consisting the isolated system or comprising this constituting the isolated system do not have any interaction with the rest part of the surrounding. This represents an isolated system or universe. So, therefore, we can write system plus surrounding means interacting system to that system. So, these are interchangeable, system surrounding. System plus surrounding comprises an isolated system or universe or isolated system. Therefore, delta S, that is a change of entropy of the system plus delta S surrounding becomes delta S of the universe or the isolated system. And just now we have seen that this is greater than 0. So, that is greater than 0 or is equal to 0. This takes care of both the things, that means the reversible and irreversible interaction. This means that within the universe, that means within this universe or isolated system, the interactions are going between different systems which constitutes this isolated system or system and surrounding. If the interaction between these constituent systems are irreversible, then delta S of the universe, that means system plus surrounding, is greater than 0. If these interactions are reversible, then it equals to 0. This can be written in a more broader sense, delta S algebraic of all interacting system, all interacting. That means, if we can define an isolated system consisting of many interacting systems, where the interactions taking place between the systems only, nothing else, so that all of them together define an universe or an isolated system, then this becomes greater than equal to 0, depending upon whether these interactions are reversible or irreversible. For reversible it equals to 0, but for an irreversible it is greater than 0. All right. Now, after this I come to this concept of delta S of a system. Delta S of a system is greater than del q by t, which leads us to think that delta S of a system is equal to del q by t plus delta Si, some positive quantity, which is always greater than 0 for an irreversible process, That means, for any irreversible process, delta S system is more than delta q by t, and which equals to 0 for a reversible process. Now, here is the concept. This definition that delta is universe, that means algebraic sum of the change of entropy of the system plus surrounding, or change of entropy of all interacting systems, algebraic sum is greater than is equal to 0. That means, it can never become less than 0. That is the principle of, this is known as principle of increase of entropy. And it is one of the very useful concept or corollary of the second law of thermodynamics, that delta S of the universe, that is system plus surrounding, can never be less than 0. It is always greater than 0 for a natural universe or for a natural isolated system where the interacting processes are irreversible, and in an ideal case it equals to 0. But for a system, as we define the change of entropy, which may be greater than 0, may be less than 0. So, now I see when delta S system greater than 0, when delta S system greater than 0, what is that? Del q by t plus delta Si has to be greater than 0. All right. Now, for a reversible process, this is 0. So, this has to be 0. Well, for an irreversible process, this is greater than 0. So, therefore, this may be greater than 0, may not be greater than 0. So, for an irreversible process, for a reversible process, delta is to be 0, because this is 0, delta q by t has to be greater than 0, which means delta q has to be greater than 0. Heat has to be added to the process. Clear? But for an irreversible process, it is sometimes asked in many interviews, very important concept, usually you may not get in all books. For an irreversible process, now if delta q is greater than 0, that means if heat is added, obviously delta S is 0. That means when, try to understand this, delta q is 0. That means if you add heat to a process in an irreversible manner, and there are also internal irreversibilities, then obviously this is greater than 0 and this is greater than 0. So, delta S system has to be greater than 0, because delta S system is this. But for an irreversible process, there are cases when even delta q by t less than 0, even it may happen. Usually this is like this is a heating process, but even if the delta q is taken out, but in irreversible case, delta q by t, if this thing is less than delta Si, the absolute value, then this will be always greater than 0. Delta S is always, have you understood this? That means if delta q by t is negative, but it cannot counterweigh the positive contribution of delta Si, then delta S greater than 0. That means that in case of an irreversible process, even if you extract the heat, entropy may increase, but in both the cases temperature increase. So, heating process, I just explained it, heating process. Now, you see, for an irreversible process, if you add heat plus the internal irreversibility, so obviously temperature will increase and it is a heating process and entropy will increase. But here even if you take the heat, but if delta Si is more than this absolute magnitude of delta Q by T, this sum is greater than 0. This is also an heating process. Here temperature increases, but heat is taken out. So, entropy is increased. These are rare situations. I just give you an example, so that in interviews if it is asked or somebody, that let us consider a mass of water. It is very important, you may not get in many books also. You stir the water, you make a paddle wheel work input, and at the same time you take heat out. Now, it may so happen if you put a thermometer that depending upon the rate of heat extraction from it and the rate of work done or the internal irreversibility is such, it is not only, it does not depend only on the work, but the dissipation. That means the fluid viscosity is such that dissipation is more, that the fluid is heated. When this exists, that means internal entropy change due to internal irreversibilities are more than this magnitude of this, then ultimate effect is the heating of the system. Though the heat is taken out, it is heated because of this irreversibility. So, some of the work is being dissipated through mechanical irreversibility into intermolecular energy, which raises the temperature. Whenever a system temperature is raised, we tell it is heated. So, whether heat is supplied or not, due to frictional heating, we tell due to friction the system is heated, no heat was supplied. It is some form of mechanical energy is being dissipated, which is known as degraded, that I will come afterwards according to law of thermodynamics, second law of thermodynamics. This dissipation is termed as degraded. Some form of mechanical energy is being degraded in terms of heat or intermolecular energy where temperature is increased. So, in this case entropy still increase. Sometimes it is asked, can you give an example where heat is being taken out of a system till its temperature, till its entropy increase? Yes. So, you can tell that entropy will increase if you give in heat to either a reversible process or an irreversible process. For a reversible process, this part is 0. So, for an reversible process, if you give heat, entropy will increase. If you take heat, entropy will decrease. There is no other way out. So, it is directly related to the heat quantities. But for an irreversible process, if you give heat, add heat to a system, definitely it will increase the entropy, because this plus this. But if you take out heat, entropy still may increase depending upon the relative magnitude of these two. In a similar fashion, I can tell the entropy of the system will decrease, system is less than 0 when del Q by T, that means there has to be a reduction, there has to be a rejection of heat, and at the same time this magnitude should be greater than delta Si. So, this is clear. So, therefore, we arrive at the conclusion that a system, the entropy of a system may decrease, may increase. A simple example is that you heat a body, its temperature will increase. You cool a body, its temperature will decrease and entropy will decrease. You heat a body, its temperature will increase and entropy will increase. You cool a body, temperature will decrease and entropy will decrease. And that depends upon the relative magnitude of the del Q by T and the delta Si. So, that both increase in entropy and decrease in entropy is possible for a system, but when you add together the entropy change of the surroundings, that means if you add up these two and find the delta is universe, it can never decrease, that it can never less than 0. It will be either greater than 0 or is equal to 0. This is clear? Okay, fine. Then next I will tell you that how we can just find some examples. Now, let us see one thing that is also very important, you may not get, I am telling you again and again in many books, that so far delta is universe. Now, I know what is the universe is, or what does it mean in thermodynamics, is greater than is equal to 0, taking care of both irreversible and reversible. At the same time, we know cyclic integral of del q by t taking care of both reversible and irreversible cycle is less than equal to 0. This is known as principle of increase of entropy, and this is known as Clausius, very good, Clausius inequality, Clausius inequality. Now, these two are same. That means, this is a consequence of this is a consequence of this with a negative sign. Now, let us understand this to make our concept very clear. Let us consider a heat engine, make our concept clear. Let us consider a heat engine, reversible heat engine. Let us consider a reversible heat engine. Let us consider a thermal reservoir at T1, at high temperature T1, and takes heat Q1 and it rejects it continuously at the amount Q2 by the amount Q2 to a thermal reservoir T2, and T1 is greater than T2, and that maintains all, respects all first law and second law, W is Q1 minus Q2. Now, we know that by this Clausius inequality, Q1 by T1 minus Q2 by T2 is 0. Clausius inequality is a straightforward consequence of the definition of absolute thermodynamic temperature scales. That means, when you recapitulate everything, the step by step all the corollaries are being recapitulated. That means, we know the definitions of absolute thermodynamic temperature scales are Q1 by Q2 is T1 by T2. So, therefore, if you represent the temperature of the thermal reservoirs in absolute thermodynamic temperature scale, then Q1 by T1 minus Q2 by T2 is equal to 0, which is nothing but the cyclic integral del Q by T. Sorry, for this thing is 0. For a reversible engine is 0, but if it is an irreversible engine, then what is that? Q1 by T1 is less than equal to Q2 by T2, and cyclic integral of del Q by T. This we have already studied before. This is because the efficiency of an irreversible engine, this is in case of an irreversible engine. Let us consider R by giving R as the reversible one. So, and this is the efficiency of an irreversible engine is less than. Now, I apply the delta S universe. Now, let us find out what is the change of entropy of the universe. Now, if I first consider a reversible engine, then considering these 3, I can consider this as an isolated system. Yes, you can argue, sir, why this is an isolated system, work is coming out. Yes, work is coming out, but at least we can consider it as an adiabatic system. So, with respect to heat interactions, it follows the same principle as that of an isolated system, because work coming out to surrounding does not do anything with the entropy. So, if you do that way, then I can tell that delta S of this entire universe consisting of this thermal reservoir T1, thermal reservoir at T2 and the heat engine must be greater than equal to 0 by this principle, greater than equal to 0. Greater than is equal to is when reversible and greater than is when irreversible. So, what is the temperature, what is the delta S of thermal reservoir? Let this is A, this is B. So, delta S A is minus Q1 by T1. If it is a reversible, then Q1 R. Now, here I am not writing Q1 R or Q2 R. Let us consider it may be a reversible or it may be an irreversible. So, what is delta S B is Q2 by T2. Okay, let us consider first the irreversible case without R suffix. What is delta S of heat engine? Please tell me. It loses heat, so its entropy changes Q1 by T1. Delta Q by T, T is constant at constant temperature minus Q1 by T1. If any doubt, you tell me. It takes heat at a constant temperature T2, so delta S B is Q2 by T2. What is delta S heat engine? What is delta S heat engine? That is system operating on the heat engine 0. Why? This is operating on a cycle. So, a system operating on a cycle continuously, its change of entropy will be 0, it is a point function. So, change of entropy in any cyclic process is 0. Try to understand what are the system. All interacting systems taken together constitute an isolated system. Here interacting systems are reservoir A, heat engine HE, reservoir B. Reservoir A undergoes a process, reservoir B undergoes a process. This is a heat rejection process. Reservoir B undergoes a heat addition process. Okay? And heat engine fluid takes heat from the reservoir A, gives heat to the reservoir B, but it operates a cyclic process. There are other processes also. That means, in a total cyclic process, the entropy change of the heat engine is 0. So, therefore, this is 0. So, with this thing, what we can write? We can write therefore, well, here itself we can write therefore, delta S universe is equal to delta S A plus delta S H E heat engine, sorry, delta S H E plus delta S B. Now, delta S A is what? Minus Q1 by T1. Delta S B plus Q2 by T2, and this is 0. So, that is Q1 by T1 plus 0 minus, sorry, it is minus, it is plus Q2 by T2. Then what it is? Minus Q1 by T1 plus Q2 by T2. What is this? Our very old known things. Again, we are getting confused. Change of entropy of A is minus Q1 by T1. Change of entropy of B is Q2 by T2. All right. So, therefore, because the entropy of A is decreased, entropy of B is increased. Okay. So, this is all right.
No, sir, there is a minus.
Where? Q1 by T1 minus. Oh, sorry. All right. Then what is this? Cyclic integral of del Q by T. And cyclic integral of del Q by T is always less than 0 for an irreversible process, is equal to 0 for a reversible process, which means delta S universe is greater than is equal to 0. That means what I want to say now, this delta S universe in a cyclic process, for a heat engine, and its thermal reservoirs its thermal reservoirs, delta S universe is nothing but minus of cyclic integral of del Q by T. So, these are synonymous things with a change in the sign. When I tell minus Q1 by T1, it denotes the entropy change of the reservoir A, that is the source. Where I tell plus Q1 by T1, it depends upon the Q by T quantity in the heating process of the working system in the engine. Similarly, when I tell plus Q2 by T2, it represents the change of entropy of the thermal reservoir at T2. But when I tell minus Q2 by T2, it represents the Q by T quantities during the heat rejection process of the system executing the heat engine cycle. So, therefore, the Clausius inequality del Q by T and delta S universe, they are what I started here. Clausius inequality and principle of increase of entropy, they are almost same. That means with a negative quantity. So, this is a direct consequences of del Q by T. That means you see, starting from the basic second law, the Carnot's theorem, that efficiency of a reversible engine is the maximum one when operating between the same temperature limits, and for all reversible engines this is an unique value when they acting between the same operating between the same temperature limits. This gives the thing that Q1 by T1 is equal to T, Q1 by Q2 is T1 by T2, or Q1 by T1 is equal to Q2 by T2. This gives rise to the fact that cyclic integral del Q by T will be 0. Then Clausius inequality comes that cyclic integral del Q by T for an irreversible cycle is less than 0. And the principle of increase of entropy also gives in the same way, because the entropy, the birth of entropy takes place through this origin, that cyclic integral del Q by T for a reversible cycle is 0, for which integral del Q by T for a reversible process is a point function, and that becomes equal to the change in the property entropy. So, therefore, delta S universe, which we have proved independently, which has to be greater than or is equal to 0, can never become less than 0, which is known as principle of increase in entropy, is almost synonymous with a negative quantity, that Clausius inequality, cyclic integral of del q by t will be other way, less than equal to 0, can never become greater than 0, because it is a difference with the sign. So, del q by t for a natural engine is less than 0, for a reversible engine is greater than 0, can never become for a reversible engine equals to 0, can never become greater than 0. Okay, all right. Now, we should have some other examples. Let us consider the spontaneous heat transfer between two bodies at T1 and T2, if they are made contact with a conducting material or through a diathermic wall, then what happens? Heat comes through. Now, let us first consider these two bodies of infinite capacities, heat capacities, is the concept of infinite thermal reservoir, sourcing. That means their temperature remains same, but T1 greater than T2. So, this is a spontaneous process, feasible process. That means T1 is higher than T2, then spontaneously heat will flow from T1 to T2. Then if I find out that let this is A, this is B, then what is delta is universe? How to find out? Universe. Now, I can define these two systems as an universe, and what is this value? Can find out delta is universe. So, universe now comprises this system A and system B. Delta is A plus. Any concept, any confusion you can ask me. What is delta is A? Minus Q1 by T1. What is delta is B? Q1 is Q2 is equal to Q. Yes, is equal to. I by mistake wrote Q1, Q2, so I rectified it by writing again Q1 is equal to Q2 is equal to Q. In examination also, if you do like that, you write this again. So, it will be what is Q into 1 by T2. For a spontaneous heat transfer from one reservoir to other reservoir without any other effect in the surrounding, as I have told, T1 has to be more than T2. So, this is greater than 0. But if it is the reversible heat transfer, what is the condition? T1 has to be T2. So, therefore, this is 0, which cannot be made. Clear? So, therefore, we see this thing that the entropy change is irreversible. Now, you come to another case, that when there are two finite systems T1 and T2, and make a simplification initially of same capacities, that means same mass, same specific heat C, same mass and same specific heat at constant pressure or volume. I am not just distinguishing it now. So, some specific heat C, some specific heat C, which is multiplied by mass, gives the heat capacity. So, that this is defined in a sense, this can be equated with the change in temperature. Okay? So, now if these two finite systems now connected, so heat will flow, and since these are finite systems, that means systems with finite capacities, if we start with T1 greater than T2, then only heat will flow in this direction. When it happens, this temperature will decrease and the temperature will increase, and ultimately they will come to a common temperature Tf. T1 will go to this Tf and T2 will go. When the temperature equalization will be there, there will be no heat transfer. So, let us consider just as the earlier case, the natural spontaneous heat transfer between two constant temperature reservoirs. Now, I consider two very simple case, that is most natural case, that two finite systems, finite capacities. So, what is this Tf? If the heat capacities are same, you know from your primary school level thing that T1 plus T2 by 2. That means this is the arithmetic mean. That means you make the energy balance. How to do it? MC T1 minus Tf, that is the heat given by this, is heat taken. So, the specific heats are defined that way. So, it may be constant volume, constant pressure, depending on the constants at which heat is being taken, at constant volume or constant pressure. We are not much bothered for that now. So, any specific heat we define, and if the heat capacities are same for the two bodies, then the algebraic sum is that. Now, what is this? Now, universe, what is universe? Consisting of this, let this body is A, let this body be B. Then you write delta S universe is equal to delta S A plus delta S. How to find out delta S A now? Tell me. How to find out delta S A? integral T1 to Tf, how to write delta Q? R mc dt by T. Now here is the concept. When I write it, while doing problems, I am okay, I can make 100% correct all the problems, do well in the exam, get marks. But after completing the exam and getting an excellent grade, now the confusion comes to me, but this is an irreversible heat transfer. Then how do I write this as an change in entropy? Because when the heat is transferred between a finite temperature difference from this body to this body, so how do you calculate the rate of heat transfer by del Q by T? Because we know that del S for a reversible process, del S for a reversible process, correct, can be equated as del Q by T, but for an irreversible process it is equals to del Q by T plus delta Si. So del Q by T, integral of that is never equals to del Q, it is less than del S, never equals to del S. So del S is greater than integral del Q by T. But why then I am doing that integral del Q by T here to find out the entropy change?
Sir,
Any answer?
sir, we
Chandra?
consider
We?
So this expression we have written for a reversible process.
Very
between the
good.
same
This expression we write for a reversible process. Very good. That means that mc dt by T is the heat transfer through a reversible process. And when you write this and finally we come up to an expression which only contains the state variables at the 2 points or 2 end states, that means it equals to the delta S. That I told at the beginning that actual process may be reversible, but if we can connect these 2 end states by a reversible process and can find out the delta Q by T for that reversible process, that defines the change in entropy for any process. Very good, I am happy. So mc dt, that is the question. So then this will be from T2 to Tf, very good, mc dt by T. So what do they give? mc ln, what is that? Tf square by T1 T2. Tf square, okay, all right, mc ln Tf by T1, oh another line, this will be mc ln Tf by T1, this will be mc ln Tf by T2. So this ln Tf by T1 plus ln Tf by T2, mc is common, constant. So ln this into this, that means Tf square by T1 T2. So this is an irreversible heat transfer, T1 is greater than T2. So this has to be greater than 0 and this is greater than 0. Why? Because Tf square is greater than T1 plus T2. Tf is arithmetic mean and T1 T2 is the square root of the geometric mean. So always T1 plus T2 by 2 is less than root over T1 T2. Geometric mean is greater than, other way around, sorry, other way down, arithmetic mean is greater than this, I am sorry, other way around. Okay, fine, this is Tf, other way around. So this minus this is greater than 0, all right. Now after this I will do another problem, that these are the classical examples. Now if we have a finite system at a temperature T1, another finite system at a temperature T2 and let their capacities are same, just a continuation of the earlier thing. If we connect this by a diathermic wall or a conducting rod, this is the expression, that they attain a finite temperature, a final temperature depending upon their heat capacities. If they are same, arithmetic mean, and we can find out the entropy change of the universe consisting of these two. But if they are connected by a heat engine, what happens? And is heat engine is reversible heat engine. So the concept is that two finite bodies at different temperatures, if connected by a diathermic wall, that is a irreversible connections. That means the transport process, that means heat transfer will take place, it is an irreversible process. But these two bodies can exchange heat via some third body, not directly, in a reversible manner. That means they can be connected in a reversible manner via a third body, that is a reversible heat engine, which takes heat from this, let Q1 and Q2. Now what happened? What is Q1? It is not constant because it is changing its temperature. That means when heat will be taken from this system, it goes to a temperature Tf, automatically temperature is going down. Similarly, this temperature is going up, and engine will automatically stop when a common temperature, there will be an opportunity when temperature will be same, then engine will be stopped, because engine cannot operate according to the second law of thermodynamics, because until and unless there is a temperature difference, a heat engine cannot operate. Heat engine cannot deliver work taking heat from reservoir of single fixed temperature. So therefore, there will be a common temperature where it is stopped, and this variation of temperature from T1 to Tf by a finite bodies does not render does not tell that the reversible heat transfer will not be there, that we can conceive of a reversible heat transfer with a varying temperature, as I have told earlier. So we can conceive of a reversible heat transfer to the heat engine, the heat addition and heat rejection, in spite of the fact the system is finite where the temperatures are changing. Now question comes, what is the value of this final temperature? This can be found out from the entropy principle. That means the same principle as I have discussed. That means let us consider this as the universe. That means delta S universe, which consists delta S, let this is A, plus delta S heat engine plus delta S B. Similar way, we can find out delta S A is MC ln Tf by T1, plus this is as usual 0, and this is MC ln Tf by T2. And if it is a reversible engine, 0. Otherwise, it is very difficult to find out. If it is a reversible engine, it is 0. So which gives ln Tf square by T1 T2 is 0. Then we see an important conclusion, that when they are connected by a reversible heat engine, their common temperature where the process naturally stops is the geometric mean of the two, provided their heat capacities are same. Okay?
Sir, please repeat this part, sir. Sir, how can we consider the entire process to be reversible? So the engine may be reversible.
Engine reversible, the heat addition process, everything is reversible, everything, because this is a concept of infinite reservoirs. That means as you consider this is changing from T1 to Tf, the working fluid or the working system also undergoes that way, that always there is an infinite small temperature difference from which the heat is transferred. That I discussed many times. So that can be considered always, that it is not that a finite system changes its temperature as it gives heat, and at the same time the working fluid of the heat engine changes its temperature as it takes heat, means an irreversible process. It is a very, very useful concept, I am telling you. So it can be, it is not that always for a reversible heat addition there has to be a thermal reservoir at fixed temperature and working fluid will also have a fixed temperature and they are equal. In exact ideal case or in an limiting case they are infinite small difference. That is not correct. For our initial understanding we do like that. It may so happen that the reservoir is a finite system whose temperature is changing. At the same time the working system in a heat engine also a finite system where the temperature is changing, so that both heat addition and heat rejection process by the working system, the temperature of the working system changes and also the temperature of the thermal reservoir changes, but also we can conceive reversible heat transfer by considering infinite type of reversers. That means I will explain that. That means for example, in this case if you want to know that very good thing, that when T1 to Tf, that means this temperature T1 it comes to Tf. So this is the way the temperature changes with time, for example. With time temperature changes for this finite system, and the heat engine system also temperature changes like that, that it always takes heat with a finite temperature, infinite small temperature difference, sorry, finite not infinite small temperature difference, and it changes T1 to Tf and it also Tf to T1. You understand? So there is a change like that. That means always it is in contact with a reservoir or that body when its temperature is infinite small different from the temperature of the working system. Is it clear? So this way we can conceive, these are the concepts, because thermodynamics does not contain big differential equations, it is very, very small algebraic steps, but while doing so you have to have the concept clear, then only you get the full satisfaction. Otherwise you may come up to an answer which is correct, but this is the concept. Very good, I am happy that you have asked this, how it can be made. So this is a reversible. So in that case I can put delta S universe 0 and I get this very useful relation, that when the two bodies of same heat capacities are in contact with each other at different temperatures, they come to a temperature, equilibrium temperature, which is arithmetic mean. But if they are connected by a reversible heat engine, they come to a temperature, equilibrium temperature, which is the geometric mean of these two. All right? Okay. Please.
We have considered the delta S of heat engine to be 0.
0. Yes.
But the working fluid inside the reversible heat engine is changing its temperature.
Okay.
Right.
And that is in one process, but it undergoes different processes and comes to the same end point. So it is a continuous process.
After completion of one process, it doesn't come to the same point.
Same exactly. That is the thing. When a heat engine operates and it stops, it has to complete a cycle. It cannot complete in between. Okay. Don't unnecessarily complicate it. You are correct that heat engine naturally stops. When the heat engine stops means it has completed certain number of thermodynamic cycles. Not like that it stops like a mechanical machines. That will be again clear afterwards. Just at any point that is stopped and it has not completed a cycle, there is a net displacement left. It is not like that mechanics thing. So it is always executing a thermodynamic cycle. So long work will be there, it has to be a thermodynamic, it has to undergo a thermodynamic cycle. You have understood? So there has to be a thermodynamic cycle always, so that delta S H is 0. Good, I appreciate your questions. Okay, then it is all right, please.
Sir, what if the heat
Please sit down and ask.
heat capacities are not equal? How do you prove the
So then you can prove there is a little complicated algebraic steps that is left as an exercise to you. Very good. Heat capacities are not equal for both the cases, that is left as an exercise. You show it to me in the next class. You do it, there is no thermodynamics in it, thermodynamics is over, that is more algebraic steps. So only some algebraic manipulations and rearrangements are there. So there is little bit algebra, not thermodynamics, that you do it. Okay, but in a simple case I am proving it to clear your concept. Okay, very good. Now after this I will, okay, next let me see what I have to do. This is all right. Now what I like to do, that very important to important property relations, okay, to important property relations. Now it is very important property relation. Here also confusion is there with many people. Property relations, I think it will not be there for you. Now recall the first law of thermodynamics. Let us recall is delta U plus delta W. Okay, or you can write du, better du, small du plus delta W. For a closed stationary system, U is the internal energy, that is intermolecular energy. Well, so there is no restriction so far in this first law of thermodynamics as far as reversibility and irreversibility are concerned. That means there may be irreversibility, and at the same time there is no such condition imposed what should be this work transfer. This may be many types of work transfer. There may be displacement work which may be irreversible displacement work, even not PdV work. There may be magnetic work, there may be paddle wheel work, this is highly irreversible work, there may be electric work. So there may be number of work transfers. Heat transfer, of course, only one type. Heat transfer defined as heat is that energy which is transferred because of a temperature difference, and du is the change in internal energy. So this is the first law, that is nothing but the law of conservation of energy. Now if I write this law for a reversible process, in a closed system, this is already there in a closed or stationary system where there is no other movement, so that change in internal energy is only intermolecular energy, there is no change in kinetic energy or potential energy. In a closed system with only PdV work, very good, PdV work, that means only displacement work under reversible conditions. Then what is the expression? Why? Because del Q is TdS and del W is PdV. Now you see that this is the first law where these two are path functions, their difference is the point function, that is the precise outcome of the first law. But for a reversible process, when I write this, then this entire equation relates only the properties, state variables. So this relationship is now treated as a property relations, or we can treat these equations as the important property relation equations for any process. For any process. That means this equation is valid for any process. Why? Because this equates only the properties. That means the change of state variables, nothing else. But where is the concept? Sometimes we are confused that this was defined with respect to a reversible process. That means a reversible process was used as a tool to define this from the first law of thermodynamics. But when we define this, then we delink this tool. That means we do not use this tool and tell that this is valid as a property relation for any process. The concept is that when the process is reversible, and the work done is PdV work, these two are synonymous. They are not independent equations. That means these two equations are synonymous. That means we can tell this is another version of the first law. If I ask that TdS is du plus PdV, under what condition this is a first law of thermodynamics? Sir, it has to be a closed system, a reversible heat transfer and PdV work. In that case, there is no difference between these two. But for any other process, which is not a reversible process, these two equations are independent, because then TdS for any other process is TdS. They have no relationship with del Q. So PdV is PdV, pressure times dV. Understand? PdV is PdV. So it has got no relationship with delta W. So therefore it will remain as it is. That means it relates TdS du PdV. That means TdS is du plus PdV. So these two are not same, and this is the first law of thermodynamics. It's okay. So therefore this is a property relation valid for any process, and this is a first law of thermodynamics. So under reversible process these two are same. They are not independent, but for an irreversible process these two are independent. This is precisely the first law, and in that case for an irreversible process this is the property relation. TdS not equals to del Q, PdV not equals to del W for an irreversible process. All right. Now another important relation, H is U plus PV, we know. So we can write dH is du plus PdV plus VdP. Okay. So dH is now du plus PdV for any process, as I have told that du plus PdV for any process equals to TdS. So I can write TdS plus VdP. So there is another relation, TdS is dH minus VdP. So therefore I have got two relations, TdS is du plus PdV and TdS is, these two relations are the property relations for any process, reversible or irreversible. But for a reversible process, this particular equation is nothing but the first law, because in that case del Q is TdS and del W is PdV for a reversible process, But for an irreversible process, this is the concept, for an irreversible process del Q not equals to TdS, TdS is TdS and del W, that means TdS and PdV can never be equated with del Q and del W, they have no relationship. Only Clausius inequality I can tell that TdS is more than del Q, that only know. And at the same time, from my understanding of reversible and irreversible process also I can tell that del W is more than PdV, because in an irreversible work transferred because of the displacement is more than the PdV. That means if you equate PdV work for a piston displacement, an actual case if you displace the piston with a finite time and measure the work done by any dynamometer, you will see that delta W is more than PdV. Okay, that is fine.